My name is Hannah Orr, and this study was characterising the vagina pressure profile using the femfit during exercise. The question we started with was, does high impact exercise promote pelvic floor dysfunction? The suggestion is that excessive or repetitive increases in abdominal pressure associated with high impact exercise may promote the development of pelvic floor dysfunction. Research assessing intra-abdominal pressure generation during different exercises report wide variations amongst individuals, and there remains no established threshold of maximal intra-abdominal pressure to guide activity restrictions. The contribution of the pelvic floor muscles to a woman's ability to tolerate increases in intra-abdominal pressure during exercise also needs to be considered. Assessment of the pelvic floor muscles using traditional perineometry tools is limited by their inability to differentiate intra-abdominal pressure from that produced by the pelvic floor muscles, rendering it invalid as a tool for measuring the pelvic floor muscles during dynamic activities. Can the femfit pressure profile help us? The femfit is a device capable of measuring a pressure profile along the length of the vagina. The device is thin, soft and flexible, with 8 pressure sensing areas, and is able to be used during dynamic and static exercise. Simultaneous measurements are made of intra-abdominal pressure at sensor 8 and within the pelvic floor muscle zone covered by sensors 1 to 6. The aim of this study was to assess the ability of the vagina pressure profile, recorded by the femfit, to describe the pelvic floor muscles during distinct tasks, by comparing it with simultaneously measured changes in the pelvic floor muscle anatomy using transperineal ultrasound. This was a prospective observational study of 18 nilipris volunteers over the age of 18 years with no or minimum non-bothersome pelvic floor dysfunction. The exercises assessed were a pelvic floor muscle contraction and straining manoeuvre in lying and standing, posterior pelvic tilt, bridge, abdominal curl, and standing holding a 13.5 kg weight. Each task was held between 5 and 10 seconds, and during each task, concurrent femfit and transperineal ultrasound measurements were performed. All measurements were taken midway through the exercise in a static position. On the top left is the pressure data obtained for a lying pelvic floor muscle contraction. To obtain the vagina pressure profile that we see on the right, the average of the pressures for the middle 2 or 5 seconds was calculated for each sensor. The sensor in the pelvic floor muscle zone that demonstrated the greatest positive pressure change for the pelvic floor muscle contraction was chosen as the pelvic floor muscle sensor for the rest of the exercises, and in this example that would be sensor 1. And sensor 8 was selected as the intra-abdominal pressure sensor. For comparison with ultrasound measurements, the pelvic floor muscle pressure was calculated by subtracting the intra-abdominal pressure from the pelvic floor muscle sensor and designated as pelvic floor muscle true. Changes in pelvic floor muscle anatomy were measured using the anterior-posterior diameter of the levator hiatus. The levator hiatus anterior-posterior was measured at rest and midway through the task. The proportional change in length was then calculated by subtracting the task measurement from the rest measurement, dividing it by the measurement at rest, and multiplying this by 100. The first question to check was the ability of the femfit to differentiate a straining manoeuvre from a pelvic floor muscle contraction in lying and standing. This figure shows a pressure profile of one participant performing a pelvic floor muscle contraction versus a straining manoeuvre. And as you can see, for the pelvic floor muscle contraction in orange, the pelvic floor muscle sensor, which is sensor 1, was high relative to the intra-abdominal pressure sensor at sensor 8, compared to a straining manoeuvre in blue, where the intra-abdominal pressure sensor 8 was higher relative to the pelvic floor muscle sensor 1. To assess the difference, a paired t-test was used, which demonstrated a statistically significant difference in pelvic floor muscle true between a pelvic floor muscle contraction and straining manoeuvre in both lying and standing. So we now have confidence in the pressure profile to differentiate the source of the pressure, unlike traditional perineometry. The second question was, can the femfit pelvic floor muscle true pressure measurement identify if the levator hiatus anterior-posterior is lengthening or shortening during the exercise assessed? Does a positive pelvic floor muscle true always equate to a shortening of the pelvic floor muscles? And does a negative pelvic floor muscle true pressure always equate to a lengthening of the pelvic floor muscles? The results suggested that a pelvic floor muscle true pressure measurement was 100% accurate at picking the shortening of the pelvic floor muscles occurring during a pelvic floor muscle contraction in both lying and standing. For the rest of the exercises, agreement ranged between 75 and 89%, with the lowest being for the straining tasks. The femfit was able to distinguish between intra-abdominal pressure and the pressure produced by constriction of the pelvic floor muscles. Incorrect performance of a pelvic floor muscle contraction is common, hence the femfit offers an exciting addition to the tools available for clinicians to assess and teach correct performance of a pelvic floor muscle contraction in both lying and standing. The femfit had the poorest agreement with the straining tasks. Closer analysis of the data suggested that a pelvic floor muscle true pressure of greater or equal to 4 millimeters of mercury always corresponded to a shortening of the pelvic floor muscles by 10% across all tasks assessed. A pelvic floor muscle pressure of less than 4 millimeters of mercury corresponded to a less than 10% shortening or lengthening of the pelvic floor muscles for all tasks. Commonly seen for the straining task was a negative pelvic floor muscle true pressure despite co-contraction and some degree of shortening, albeit less than 10%, of the pelvic floor muscles. This was frequently associated with bladder neck descent on the ultrasound images. Further studies that include vaginal wall descent measures as a second variable alongside changes in the pelvic floor muscles would likely add value in understanding the changes of the pressure profile in these situations. In conclusion, the femfit was able to distinguish between pressures developed in the region of the pelvic floor muscles and intra-abdominal pressure, with a pelvic floor muscle true of greater or equal to 4 millimeters of mercury corresponding to a 10% shortening of the pelvic floor muscles across a series of tasks. It is the first measurement device to offer independent pelvic floor muscle and intra-abdominal pressure biofeedback during dynamic exercise activities.